So in this video, we're going to explore polynomial functions and their behavior when graphing them. So we kind of, in the previous video, looked at what a polynomial function is, how to tell what the degree is, and what the leading coefficient is. So now we want to explore, we also looked at the end behavior. Don't want to forget that. So now we want to explore what is the behavior in the middle. How do I know that when I graph it, it's going to look like this? So we kind of graphed it and we saw it made it look like this, where it went, the end behavior went up. Then we had these smooth curves, was continuous, and then the other, when we go to the right, it went to positive infinity. So how do we know this behavior? How do we know where the zeros are? So we want to be able to find the intercepts. So when you talk about the zeros of a polynomial function, you're talking about the x-intercepts. The x-intercepts are also called the roots, also called the solutions. And just like before, if we want to find the x-intercept, what you do is you let the output equal 0 and you solve for x. So if this is our function that we were exploring, I let the output equal 0. So that means instead of writing f of x here, I'm going to put 0. And then I'm going to solve for x. So I'm going to take a look at this. They have a greatest common factor of x squared. I can pull out an x squared, factor it out, and I get this. And then I can set each of these equal to 0 and solve for x. Here I'll get 0, and here I'll get x squared equals 4, or x, taking the square root of both sides, has to equal plus or minus 2. So I will have x equals 0, x equals 2, and x equals negative 2. Those are my roots, or my solutions, or my x-intercepts for this function. And so when I look at the graph of the function, I already know that both as you go far to the left and as you go far to the right, I will have this end behavior. And now I know also that I will have an x-intercept at negative 2, at 0, and at positive 2. So that's going to help me, it's going to be part of the puzzle in order to draw this graph. And so that's why this graph of this will look like this. And so also take a look at this and you see that at this positive 2, the line, the curve goes through. Then there's a turn here, and then at this 0, it doesn't go through, it just goes, it touches, and then it goes back. And then at negative 2, it crosses. So there's reasons why that it crosses or it touches. And that has to do with the multiplicities of the function. And so if I wrote this in factored form, I would see, when I factored this, I had x squared times x squared minus 4. But I could factor this further, x squared, I don't really need the parentheses here, and then factoring this difference of squares, I could write it like this. So we can see our zeros, you set each of these equal to 0. This one has what's called an even multiplicity, because really I could write the factored form like this. So there are going to be 2 x's that would set equal to 0, and then these 2 are only set equal to 0, 1. So we have like a double root here, kind of a double root. So if your root has what's called an even multiplicity, then it's going to touch the x-axis and turn around. At that root. And if on these two, these have one solution each. And those are odd. It's just a single root. So it's an odd number. So if, for example, let's say when you factored it, right now these have odd multiplicities, and this one, when we saw it before, had x squared, meaning it had an even multiplicity. If the problem had, one of them had x plus 2 cubed, that's also an odd number, so that's called an odd multiplicity. And so that would also do the same thing here. We call it an odd multiplicity. And if it has an odd multiplicity, then what it's going to do, it's going to cross the x-axis at that root. This should say root here. So regardless of whether the multiplicity of a 0 is even or odd, graphs tend to flatten out near zeros with a multiplicity greater than 1. So if you did have a multiplicity that was a large number, you will see them kind of flatten out there. So this one, you kind of see it's more flat, curves around, because it has a higher multiplicity. But it touches and then turns around. So just talking about some of the characteristics of a graph and how the graphs are formed. So, and then also, another thing I want to point out is that when you look at the degree, so here we have a degree of 4. The degree is going to help us determine the number of turning points. So what do I mean by turning points? The turning points are how many times you see it kind of turn. So here I have 3 turning points. And if you have a polynomial function of a degree, in this case 4, then the graph is going to have at most 1 less turning point. So at most here would be 4 minus 1. I'm going to say n in general for the degree. So this is going to equal the number of turning points. And that's at most. So you could have less, but at most, in a 4th degree equation, at most I would see 3 turning points, and that's what I see here. A turning point, the definition is where the graph changes from increasing to decreasing, or vice versa, decreasing to increasing. So like here, we're seeing it go down, and then we see it go up. That's considered a turning point. Here we see it go up, and then we see it go down. That's a turning point. And then we see it go down and then up again. That's a turning point. So those are considered the turning points. So when you're graphing these turning points, yes, we're going to use our calculators to graph it, but you can kind of, from looking at the polynomial itself, you can see, you can use the leading coefficient test, which was talked about in the prior video. You can look at to determine the end behavior. So you can just look at the polynomial and you can see what's my leading coefficient, what is the degree, is it even or odd? And that's going to help me. Let me grab that table that we kind of drew out. I can tell the end behavior. Then the next thing I do when I'm looking at a polynomial is I look at the roots. Set it equal to 0, solve, look at the roots. If that will tell you where it's going to either touch or cross the x-axis. If it has an even multiplicity, then it's going to touch at that root and turn around. And then if it's an odd multiplicity, then it's going to cross. The higher the multiplicity, regardless, even or odd, the graph's going to flatten out near that root if it's a high number. And then the other thing is that you can find the y-intercept. You can find the y-intercept by taking the function, just like previously, and you evaluate it at 0. So my function was x to the 4th minus 4x squared. So in place of the x's, I'm going to evaluate the function at 0. Now in this one, when I plug in 0, 0 to the 4th is 0, 0 squared is 0, and then multiply by 4, still 0. So 0 minus 0 is 0. So you're going to have a y-intercept at 0, and which is what we saw here. Where does it cross the y-axis? Right here at 0. And then you can use sometimes some symmetry to help you fill in the pieces of the graph. We know that if you have a polynomial, it's smooth and continuous. There's no holes, no breaks. And then also the last thing is that you look for those turning points. How many turning points could you have? And that's going to help you check whether or not you've drawn it correctly. So that is how to graph a polynomial function. Let's take a look at this. So this problem says to determine the end behavior of this polynomial function. And so when I look at this function, I first look, if I want to determine the end behavior, I'm going to use the chart that I showed you, and I'm going to say, what is the degree and what is the leading coefficient? And so the degree here, we have 4 terms. Remember, terms are separated by a plus or minus sign. The degree here is 4. The leading coefficient is 1. So using the chart that I gave you, let's take a look at it. We have a positive leading coefficient of 1. We have an even degree. So I'm expecting the left and the right side to increase without bound. So in answering this question, when you see where does y go, you're going to say as x goes to infinity, so this is to the right, going, when you're talking about x going to infinity, you're talking about x going to the right side, the far right. And so y increases. So according to our chart, y is going to increase. And then as x goes to negative infinity, that means that x is going to the left, far left side. We're going to see y increase without bound, which means it goes to positive infinity. So that's how you would answer that type of question. The next question we're going to practice. Find all the real zeros. So what do I do here? I'm going to plug in a 0 for my output, and then I'm going to factor this side. And you may say, well, how am I supposed to factor this? We're going to try factoring by grouping. When you factor by grouping, you're going to look for the greatest common factor among these. So I'm gonna factor out an x squared. I'll get 2x minus 1. Here I have to factor out, they have a negative sign there, so I have to factor out a negative 16, and I'm going to end up with 2x minus 1. So the factored form would look like this. Now set each of those equal to 0 and solve, and I'll get my 3 roots for this polynomial function.